Good day everyone, so welcome to the week 5 of our chemistry course. For this week, our topic is quantum theory and structure of atoms and electronic structure and periodicity. Okay, so the title is quite long, but let's proceed. For this week's lecture, we will be giving a brief introduction to quantum theory and the development of periodic table. Okay, so apart from this, the different physical and chemical properties of the elements will be discussed in detail. We will learn more about how ion radius, atom radius, and electronegative and charge influence the properties of the elements. Okay, so basically, the concentration of this week's topic is quantum theory and the development of periodic table. Okay, so at the end of this module, you will be able to, number one, understand how energy is quantized. Number two, explain the Debye and Bohr's model. Number three, understand quantum mechanics. Number four, identify the different quantum numbers. Number five, determine different kinds of atomic orbitals. Number six, learn how to write and understand electron configurations. Number seven, enumerate the different groups of elements. Number eight, discuss how ionic radius, atomic radius, and electronegative charge affect the properties of an element. Number nine, identify the different variations in the physical and chemical properties of the elements. And number 10, learn the general trends of elements in a periodic table. Uh, for the first half, which is the quantum theory, right? So I'm afraid we have no introduction for that, but let's proceed. Planck's quantum theory. Okay, so Max Planck, a German physicist, discovered that energies are being absorbed by atoms and molecules only in small amounts. He defined the smallest quantity of energy that can be absorbed through electronic radiation as quantum. Okay, so that's the smallest quantity of energy. The energy E of a particular quantum of radiant energy is described as E is equals to h times V, where h is Planck's constant, which is equal to 6.63 times 10 raised to negative 34 joule seconds. And V is the radiation frequency. Okay, so E is always expressed in integral or whole number multiples. Radiation frequency, the most common radiation that we know is first gamma rays, uh, alpha, beta rays. Okay, so each type of radiation has a different frequency. So that's V. Shortly after 5 years, Planck proposed the quantum theory. His hypothesis was used by Albert Einstein to explain another theory, which is the photoelectric effect. This theory explains that when certain metals are exposed to light of at least a certain minimum frequency, okay, which is also called the threshold frequency, electrons are ejected from its surface. Okay, so no matter how intense the light is, no electrons will be ejected if below the threshold frequency. If above the threshold frequency, the brightness of the light is directly proportional to the number of electrons ejected, while the energies of the electrons are directly proportional to its frequency. Okay, so again, notice the difference. Planck's sorry, Planck's quantum theory is about the energy absorbed, the smallest energy absorbed, which is quantum energy. Albert Einstein's photoelectric effect is electrons being ejected on metals, okay, on the surface of metals when light or when it is exposed to light. So again, we mentioned threshold frequency and everything. We will discuss it more on the next slides. So using Planck's quantum theory, Einstein stated that energies are also possessed by each photon, described as E is equals to hv. Photon is the particle of light, where v is the frequency of light. Okay, so this is the same formula from Planck's quantum theory, but instead v is the frequency of light. Here is a representation of graphic representation of photoelectric effect. Okay, so the red example, by the way, on the bottom text here, this metal is potassium, and we need two electron volts needed to eject electron. Electron volts is a unit of energy. Okay, so that's a type of energy. This is the unit being used usually when we deal with electrons. Okay, so on the red example, this light wave has 1.77 electron volts energy. Notice that when it hits the surface of the metal, there will be no electron that will be ejected since it is below the threshold frequency, which is 2. Okay. On the next example, the green one, the energy of the light wave is 2.25 electron volts. It is above the threshold energy. Therefore, an electron will be ejected on the surface of the metal. Same with the blue example. It possesses 3.1 electron volts, way above the minimum, so an electron will be ejected. Also notice that 2.25, 3.1. Okay? So the rate or the velocity of the electron when it was ejected is also proportional to the energy of the light wave. Okay? So this one is has higher energy, faster electron. Lower energy than this, so slower electron. Alright? In 1913, by the way, this is Bohr's theory of hydrogen atom. In 1913, Niels Bohr, a Danish physicist, postulated that the electron moves around its nucleus in circular orbits, which can only have certain allowed radii. The electron is only allowed to occupy orbits of specific energies. Okay, before we proceed to this one, so for you to be less confused, we are talking about this one. Okay, from the nucleus, there will be orbits, okay, in which the electrons move or revolve. Okay, so each orbit is counted. So this is n is equals to 1, 2, 3, and so on and so forth. Okay, let's go back to the formula. So energies that an electron and hydrogen atom can occupy is expressed as E sub n is equals to R sub h times 1 over n squared, where R sub h is the Rydberg constant for the hydrogen atom, which is equal to 2.18 times 10 raised to negative 18 joules. N is the principal quantum number as I've shown on the illustration. It is usually represented by an integer, meaning a whole number, which is 1, 2, 3, and so on. N decreases as the electron comes closer to the nucleus. Okay, so the closest to the nucleus is 1, then 2, then 3, and so on and so forth. Some definition of terms. Negative energy means that the energy in an electron of an atom is lower than the energy of free electron. A free electron is an electron which is infinitely located far from the nucleus. The energy of a free electron is zero. What it's trying to say is that when we say free electron, that is an electron which is very, 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 very far from the nucleus. And then energy, okay, when we say energy, we refer to the energy in which the nucleus pulls the electron. So when an electron is very near to the nucleus, of course the pull will be very strong. It will be a very high energy. Since our free electron is very far from our nucleus, so the pull is very weak, which is almost zero. That's why the energy of a free electron is zero. Negative energy, of course, that is energy that is lower than that of the free electron. That's why it's negative. Next, ground state or ground level is defined as when n is equals to 1. This is the most stable energy state. Okay? This is the first quantum level, which is the closest to the nucleus. It is said to be the most stable because the pull of the nucleus is very strong on this quantum level. It's very close. Okay? Excited state or excited level refers to the state or level which have higher energy than the ground state. Okay, that is the quantum levels greater than 1. So n is equals to 2, n is equals to 3, and so on and so forth. It is said to have higher energy or a more excited state because since it is farther from the nucleus, the pull of the nucleus is weaker, so the energy needed to pull those electrons is less. Okay, and the processes will have higher energy because of the more frequent exchange of electrons. So that's what we're trying to say in here. The farther away the electron is from the nucleus, the higher the excited state is. However, Bohr's model cannot explain the spectra of atoms which are heavier than hydrogen. So this is the limitation of the Bohr's model. Okay, so it usually just applies to hydrogen. Anyway, this is the visual representation of the Bohr model, which we have discussed just now. Okay, in 1924, Louis de Broglie, a French physicist, stated that if light waves behave like a stream of particles, then electrons can have wave properties. Okay, what do you call this one? It is established that light has wave-like properties, right? Okay. What Louis de Broglie is saying here is that since according to Einstein's photoelectric effect, since an electron can be affected by light, which is a wave-like particle, therefore electrons should also be having wave-like properties. So wave effects or affects wave. Okay, so electrons act like a standing or stationary wave. He also stated that if electrons in a hydrogen atom acts like a standing wave, then the length of the wave must exactly fit the circumference of the orbit. I saw this one. So the electrons in an orbit or in a quantum level is actually not moving in a perfect circle since it has wave-like properties. It will move in a wave-like motion, but okay, it follows an orbit. It is not a perfect circle. It is a wave-like property, of course. It is a wave-like shape. I mean, so this one. Okay, so the boy and the Bohr model. Waves on a string, letter A. Waves on a string have a wavelength related to the length of the string. Okay, so you can see this when you have a string, then you vibrate that string, it will act in a wave-like motion. But the wave-like motion is limited to the length of the string. So what we're trying to say here is that letter B, if we imagine the string bent into a closed circle, we get a rough idea of how electrons in circular orbits can interfere constructively. So this one, so if this is a string and then we vibrate that string, okay, it will move in a wave-like property but in a circular shape or circular orbit or something like that. So that's what the boy uh, is proposing. If the letter C, if the wavelength does not fit into the circumference, then the electron interferes destructively. It cannot exist in such an orbit. Okay? So only the electrons, what do you call this one? The electrons with the wavelength that fits the orbit should be in that orbit. Okay? So that's the proposition. Bohr's theory, so we are now on quantum mechanics. Bohr's theory was a significant finding with regard to the atomic model and specific energies of electrons in particular, but it did not account for the particle and wave-like properties of matter and atoms having more than one electron. Okay? So the quantum mechanical model was then proposed by Erwin Schrödinger, where he defied the previous suggestion that an electron moves around the nucleus in a defined path. Instead, he focused on the idea that an electron moves like a wave. So this is the more refined proposition. Such behavior of electrons makes it impossible to pinpoint its exact location and path, which was further defined through the Heisenberg uncertainty principle. Okay? This principle explains that it is uncertain to know both the momentum and position of a particle. Momentum, represented by P, position, represented by X. So delta X and delta P are uncertainties of the position and momentum. Such conclusions make it impossible to attempt physical measurements of an electron's position and momentum. Although we may never be able to identify the exact position of an electron in an atom, we can still locate a specific region where it can be found. Okay? So, position, impossible. But we can predict the region or the area where we can find the electron. Electron density describes this probability where a particular region in an atom can be identified. This region is further illustrated through atomic orbital or a wave function, in which a given volume in space around the nucleus is said to be where an electron is most likely found. An orbital is bounded by three parameters called quantum numbers, describing the energy and three-dimensional region around the nucleus where an electron can be found. Okay. So before we should we discuss first or should I show you how it looks like first? Let's see. Okay. Let's see. Okay. So I guess we should discuss first before we show you this illustrations. So three quantum numbers are used to the size, shape, and orientation in space of orbitals where electrons can be found. So first we have the principal quantum number, which we have discussed earlier, the angular momentum quantum number, and the magnetic quantum number. So the principal quantum number N, angular momentum L, magnetic M. Okay. So one quantum number explains electron behavior, which is the spin quantum number denoted by S. All numbers combined complete the quantum number describing a specific electron. Okay. The principal quantum number, or N, describes the size of the orbital. It also indirectly describes the energy of an orbital. Okay. Next, we have the angular quantum number. We will describe each first before we show the how they correlate to each other. The angular quantum number, denoted by L, describes its shape. It can either be spherical, okay, polar, or clover leaf. L is equals to 0, equals to 1, equals to 2, and so on. More complex shapes can happen as this number goes higher. The value of L is designated by letters such as, okay, this is L is equals to 0, 1, 2, 3, 4, 5, and so on. So uh, the letters to represent these quantum numbers are S, P, D, S for 0, P for 1, D for 2, F for 3, and then after F, it goes alphabetical. Okay? As the angular quantum number increases. Alright, next we have the magnetic quantum number. This describes its orientation. So unlike spheres, orbitals with polar or cloverleaf shapes can point in any direction. Then lastly, the spin quantum number describes the electron spin either clockwise or counterclockwise. Right? So in writing these numbers, these are the rules. Quantum numbers are integers. All quantum numbers are integers. Okay? 0, 1, 2, 3, and so on. The principal quantum number, which is n, cannot be 0. Again, the smallest atom is hydrogen, and hydrogen has n is equal to 1. It has 1 electron, so it has 1 orbital and 1 quantum level. So there's no element with 0 principal quantum number. So it is 1 and above. Next, the angular quantum number is any integer between 0 and n minus 1. Okay? Remember this n minus 1. The magnetic quantum number, which is m, is any integer between negative 1 and positive 1. Or, okay, we will discuss more about this later. And spin quantum number is either positive 1/2 or negative 1/2 depending on the direction. Clockwise, counterclockwise. Next. With the three quantum numbers identified for any atom, we can now determine the number and structure of orbitals it may have. The table below details all possible combinations of the quantum numbers. Okay. So we have here, this is the principal quantum number. We can also call that a shell. Angular quantum number, we can also call that subshell. This is the angular quantum number in letters. Then we have the magnetic quantum number, or m, this one. And then we have the number of orbitals. Okay, let's start with n, or the shell. This is the principal quantum number. So this is the number of major quantum levels. Okay, for each quantum level, there will be subshells, or the angular quantum numbers. So, for example, hydrogen, which has n equals to 1, it has 0 subshell. Okay, because n minus 1. Remember the rules earlier, the previous slide. Angular quantum numbers is between 0 and n minus 1. So our n here is 1. This is 0. Okay, so in notation, all s will be denoted by 0. Again, all zeros are denoted by the letter S. Okay. And then, the magnetic quantum number will depend on the subshell. So 0, 0. Number of orbitals, 1. Okay. Next, we have the number of orbitals, depends on the magnetic quantum number. So next, if we have two quantum levels, or n is equals to 2, we will have two subshells, 0 and 1. Again, n minus 1. 0 is denoted by S, 1 is denoted by P. Okay, then for the orientation on P subshell, okay, which is L is equals to 1, we have negative 1 and positive 1 as possible magnetic quantum numbers. Since we have negative 1, 0, and positive 1, we have now 3 orbitals. Okay? Now let's proceed to n is equals to 3. We have an additional subshell here, which is 2. Sorry. So 2, n is equals to 2 will be denoted by letter D, and then negative 2, positive 2, So the number of orbitals will be 5. And so on and so forth. 4, 3, 3 is denoted by F, and then negative 3, positive 3, altogether is 7. When we have n is equals to 5, we have a L is equals to 4 subshell, which will be denoted by G, then negative 5 to positive 5, then that will be 11. That will be 11. Okay, so that's it. Next, sorry. Atomic orbitals are illustrated through a boundary surface diagram depicting the regions where 90% of total electron density is found. Detailed below are the boundary surface diagrams of the different quantum number combinations and thus the orbitals. So this will be the shape of each subshell or angular quantum number. So for S, it's shaped like a dome, okay, or spherical. Spherical shape. Okay, so what is shown here is half. Then n is equals to 1, n is equals to 2, n is equals to 3. Or sorry, every color is 1 n. So 1, 2, 3, 4, 5, 6, 7. Okay, and so on. For P, the shape is this one. Dipole. Was it dipole? I think the term earlier was dipole. Okay. So P sub Z, P sub X. These are all P, but the orientation are different from each other. Okay. Then for D, it is shaped like a four-leaf clover. Okay, four-leaf clover, four-leaf clover. This one is also this is not a four-leaf clover since this is only on one plane. But anyway, that's it. And then when we proceed and we have more subshells, the shape is getting more and more complex. So for the atomic orbitals, all s orbitals are spherical in shape, so they differ in sizes, becoming larger as the principal quantum number increases, as we've shown from the illustration. The p orbital, or all p orbitals, are polar or dumbbell-like in shape. Yeah, dumbbell. Why did I mention dipole? Anyway, it has two lobes on opposite sides of the nucleus. All p orbitals look the same, except for their orientation in space. They also become larger as the principal quantum number increases. Let's go back to the illustration. So this is P. Okay, so n is equals to 6. We have smaller dumbbells in here, and it increases as the quantum number or quantum level increases. Okay, then the orientation changes depending on the plane that it is oriented. The orbitals. All the orbitals compared to S and P has two different shapes. Four of them assumes the cloverleaf shape with four lobes. One is like P orbital but with a donut-shaped region in the xy plane. All other orbitals of higher principal quantum numbers have more complex shapes and combinations. Okay. Orbital energies. So energy levels for orbitals determine the actual arrangement of electrons in atoms. Electrons will first fill the most stable orbitals. Okay, so these would depend not only on the principal quantum number and the angular quantum number, but also to certain properties such as repulsion between electrons and orbitals and total energy to use in order to fill an orbital. In summary, okay, so here is the order in which the electrons are filled in our atoms. So first, the electrons will fill the slot for 1s, then for 2s, then for 2p, 3s, then 3p, 4s, 3d, 4p, 5s, and so on and so forth. Okay, so this is how the order in which the electrons fill the atom. So if we have an atom which has so many electrons, like the very heavy ones, the lower part of our periodic table. Okay, so I think it will reach this level. So it has to follow this order. Okay, these ones should be filled first. Next, with all four quantum numbers, we can now determine all orbitals possibly being occupied by electrons in an atom through the electron configuration. The electrons fill the orbitals through a scheme called the off-bow principle, which deals with increasing energy of subshell. So this is the what is being denoted in the illustration earlier. Okay. And then for our periodic table, so this is the summary, or this is the pattern in the periodic table in terms of quantum arrangement. Right? So this area, if the electron is found in this area, meaning the last electrons is on this level. For example, the element here, the last or the outermost electrons of this element is found on the 6s subshell. If you have an if you have an atom in here, its outermost electrons is found on the 3p subshell. So this is what it means when it comes to our periodic table. Hydrogen, helium. Okay, so they only have one quantum level. So the outermost electrons is found on the 1s subshell. Okay, in writing, write the orbitals occupied by electrons, the numbers in subscript for each orbital to identify the number of electrons. For example, we have hydrogen. So hydrogen only has one electron and it is on the 1s subshell. So 1s with 1 as the superscript since it has only one electron. If that is helium, then that will be 1s, superscript is 2 since it has 2 electrons. For nitrogen here, okay, nitrogen has 2, 4, 6, 7. The atomic number of nitrogen is 7, so it has 7 electrons. And we will follow the pattern on how it fills the, or we will follow the off-bow principle on how the electron should fill in the atom. So first, it will fill the 1s, then 2s, then 2p. Okay. So 1s, 2, 2 electrons, 2s, 2, 2 electrons. We have 3 electrons for p. So p sub x, p sub y, p sub z, and so on and so forth. Sorry. Another way to write placement of electrons is an orbital diagram in which each orbital is represented by a square and the electrons as arrows pointing up or down. In Hund's rule, when electrons are placed in set of orbitals of equal energy, they are spread out as much as possible to give us few paired electrons as possible. Okay, so I'll go back a little bit. So you might be wondering, so this is the number of orbitals or the number of electrons in a subshell. So for no, never mind. This one. Okay, so for each orbital, there will be 2 electrons. So for an s, the maximum is 2. For p, the maximum is 6. For d, maximum is 10. And so on and so forth. Okay. So in this case, for our example earlier, for nitrogen, since the maximum electrons in the p subshell is 6 and we only have 3, we have to fill each of them first, okay, before we proceed to the next one. In the case of oxygen, the atomic number is 8, so X, Y, and Z should be filled with 1 electrons first, then the X will now have 2 electrons since each of them was already filled, right? So that's how the electrons are distributed in each orbital. Okay, so rules for assigning maximum number of electrons to orbitals. Number 1, the principal quantum number also dictates the number of subshells. The number of orbitals is determined by the angular quantum number, and only 2 electrons can be placed in each orbital. Use 2n squared to compute for the maximum number of electrons an atom can have. Okay? So if an atom has 3 orbital, so 3 squared is 9 times 2, it can have 18 electrons maximum. This one, 1, 2, 3, we can find it in the table on quantum levels earlier. The following describes properties of electrons in atoms based from their electron configurations. Number 1, Pauli exclusion principle. No electrons in an atom can have the same combined quantum numbers. Number 2, each orbital can only have 2 electrons with different spins. Oh. Number 3, Hund's rule. Arrangement of electrons with the highest number of parallel spins are the most stable. And then number 4, atoms with unpaired electrons are paramagnetic, while atoms with paired electrons are diamagnetic. Okay. In hydrogen, number 5, the energy of the electron is the principal quantum number. For other non-hydrogen-like atoms, the energy depends on both N and L. L is the angular quantum, or the subshell. N is the shell. In atoms with same N, the smallest L is nearest to the nucleus, and therefore harder to break as compared to the higher L or higher subshell. Okay, so that's it for our quantum theory. So we're done with our quantum theory. So next, we will discuss about our periodic table of elements. Okay, so this one, we had an introduction video earlier. So I hope you still picked up some of the stuffs from our introduction video. Anyway, so the development of the periodic table began during the 19th century. The discovery of atomic masses of each element allowed chemists to organize the different elements in a periodic table. Furthermore, chemists believed that by grouping them on the basis of their atomic masses, they were also able to cluster elements with the same chemical behavior. This was based on the rationale that chemical behavior and atomic mass had a strong correlation. A few chemists had tried to decode the relationship of each element according to their atomic mass and other relevant properties. John Newlands in 1864 attempted to explain the relationship of the elements on his law of octaves. The law of octaves explained that when the atomic masses of the elements are arranged in ascending order, elements falling in every 8th position were deemed to have the same properties. The weakness of Newland's law of octave was its inapplicability to other elements beyond calcium. So it was discarded. The work of Dmitry Mendeleev and Lothar Meyer provided a more encompassing tabular arrangement of the elements in a periodic table. It was in 1869 that the two chemists developed a classification system that addressed the inadequacies of earlier methods of arranging the elements. Mendeleev was able to enhance the law of octaves in two important ways. Firstly, the new classification of system of Mendeleev allowed the elements to be grouped together in a much accurate manner. Secondly, it allowed the prediction of the properties of unknown elements, such as in the case of gallium. The element gallium, prior to its discovery, was called Eka-alu-imo. Uh, Mendeleev, using his proposed classification system, had predicted a few of the characteristics of gallium. In the time gallium was discovered, its predicted properties was indeed very much similar to its actual element properties. Though Mendeleev's work paved way to better classification system, several inconsistencies were documented. This led to the discovery of other element property that influencing the arrangement of the elements in the periodic table. This essential property that affects arrangement of elements was the atomic number. Henry Moseley elucidated the role of atomic number and how it influenced the arrangement of the elements in a periodic table. Moseley discovered that the atomic number had the same pattern as atomic mass. It increases in a similar manner with atomic mass. The contribution of Moseley provided a way in reorganizing the elements in a more accurate and logical manner, such as in the case of argon. Figure below shows the periodic table of elements. Okay. Let's proceed to the periodic table of elements. We have some classifications in here according to the color. Okay, so this one is the alkali metal, alkaline earth, transition metal, basic metal, metalloids, nonmetals, halogens, noble gases, lanthanides, actinides. Okay, so these are the major classification. We have more major classification in our uh, periodic table. We have the transition metals. Let's see. I think it was mentioned here. Okay, the four major categories of the representative elements, the noble gases, the transition metals, the lanthanides and actinides. Okay, so the chemical activity of the four types are determined by their valence electrons. The valence are the outermost electrons. Okay, so again, representative elements, noble gases, transition metals, lanthanides and actinides. Noble gases, transition metals, lanthanides and actinides. The rest are representative elements. So those are the four major classification, and then these are the more specific classification of a group of elements in the periodic table. Next, so the representative elements are also known as the main group elements. So they belong to group 1A to 7A. 1A to 7A. 1A to 7, 1A, 2A, 3, 4, 5, 6, 7A. Okay, so these are the representative elements. Elements in this group have S or P shells that are not completely filled. Valence electrons occupy the highest N shell. Valence electrons pattern showed similarity among this group of elements. It can be observed that all representative elements have the same number and type of electrons. So we have, as we've seen earlier, the subshell classification of periodic table of elements. So the representative elements have S or P shells, okay, as their outermost subshell. Noble gases, this is the last column. They are the group A elements. They are characterized by a completely filled P subshell except for helium, which is a completely filled S subshell. Elements in this group has an electron configuration of NS2 or NP6, meaning the S subshells are filled and the P subshells are filled. Okay. Only helium has a different configuration compared to other noble gases, since it is 1s2. Noble gases exhibit almost similar behavior. Okay? These elements, such as in the case of helium and neon, are fairly stable that can be attributed to their completely filled Ns and Np subshells. So the most interesting characteristic of noble gases is that since the outermost subshells are filled, right, they have no valence electrons, or rather, they have no, uh, they are very stable. They have no excess electrons or excess space that they can accept electrons. So they can neither, almost neither, accept nor give out electrons since the whole subshell is filled. It is very stable. Next, transition metals, also known as the D-block transition elements. So these are the elements in group 1b and 3b to 8b. So let's go back to the periodic table. So 1b, uh, 1b, 2b, 3b, 4, 5, 6, 7, and then 8. These are transition metals. This group of elements can be differentiated from other elements in the periodic table by observing their d subshells. Transition elements have incompletely filled d subshells as well as readily produce cations with incompletely filled d subshells. Another characteristic is that valence electron configuration is not always similar within the group. So next or lastly, we have the lanthanides and actinides, so referred to as the F block transition elements. So the F subshells are incompletely filled up. So notice that the major classifications are classified according to the subshells, the outermost subshells. Okay. Periodic variation in physical properties. Physical properties of elements may vary among the different groups of elements. These variations in their physical properties have effects on the behavior of elements. The subsequent section will discuss the effective nuclear charge, atomic radius, and ionic radius as the essential periodic variations that have effects on physical properties of the elements in the periodic table. Okay, so these are the following physical properties of elements which can be observed through the periodic table. So first is the effective nuclear charge, or Z sub EFF, is the nuclear charge felt by an electron when both the actual nuclear charge and the repulsive effects of the other electrons are taken into account. Okay, so it can be determined using Z sub EFF, or Z is equals to Z minus, uh, forget the Greek letter. So this is sigma. Okay, small letter sigma. So Z minus sigma, or shielding constant. Okay. So the proximity of the core electrons to the nucleus as compared to the valence electrons allow greater shielding effects on valence electrons. This is in comparison on how valence electrons shield one another. The trend of effective nuclear charge is increasing as one goes from top to bottom of a particular group of elements in a periodic table. So top to bottom, increasing nuclear charge. Next, atomic radius. It is the basis in defining the size of the atom. Okay. Referred to as one half the distance between the two nuclei in two adjacent metal atoms or in a diatomic molecule. So figure below shows the predict trend of atomic radii of each element. Radius, okay, in a circle from the center to the outermost part. Okay, so as you can see, the trend here is that from top to bottom, the atomic radii increases. From right to left, atomic radii increases. So So that is the trend in the periodic table. Top to bottom, right to left. In summary, atomic radius is one of the distance between the nuclei into adjacent atoms. If you're still curious about this one, what it's trying to say is that when we have two atoms beside each other, okay, so this will be the nucleus, this will be the nucleus. Of course, they will have a distance between each other, these two nucleus, and one half of that is the radius, okay? If you're still wondering what this statement is about. Given that these atoms form an extensive three-dimensional network. Furthermore, the atomic radius of elements with simple diatomic molecules is one half the distance between the nuclei of the two atoms. Okay, good one. Next, you have the ionic radius. This is referred to as the radius of a cation or an anion. The size of an ionic compound is influenced by the sizes of its cation or anion. When an atom acquires an additional electron and forms an anion, the electron cloud sphere expands. This happens when nuclear charge stays the same and the repulsion to the expansion of the electron cloud. On the contrary, a reduction in the number of the electrons in an atom leads to a decrease in the size of the electron cloud domain, resulting to a smaller cation. Okay, as we've discussed earlier, cations and anions. So cations are the more positive and anions are more negative because anions has excess electrons, cation has missing electrons. When we say excess electrons, for example, if we have a P subshell or if we have S subshell, remember that in an S subshell we have two electrons, right? And then if rather let me do this this way. If we have a P subshell in here and it has a P subshell should have 5, right? 6 I mean. For example, move this one. This one has an excess electron. When we say excess electron, since if this electron will be gone, this one should be more stable. Okay? In this case, if we add an electron here, this will be filled, so this will be more stable. So this one has an excess, this one is lacking. This is an ion, this is cation. Okay? So when we remove this one, for example, it has another subshell on the inside. Then this is the nucleus. If we remove this electron, donate it to this one, there will be no electrons in here. So this orbital will be, or the subshell will be not needed anymore since there will be no electrons. Okay, so since it will be not needed anymore and this one has, let's say, 2, let's say this is an S subshell. So this subshell is complete, it is now stable. Okay, so that is the effect of exchanging electrons. When an element with excess electrons will donate, it will now be more stable. When an electron with missing electrons will accept, it will now be more stable. Okay, but as you've noticed, this is supposedly the original orbit, right? But after donating, the orbit will disappear. So the atom will have a smaller radius. That is ionic radius. That is not atomic radius. Okay. And this one, no change. So that is the ionic radius. The radius of the electron or the atom changes depending on, or usually after it donates or accepts an electron. Okay, so this one. Then next. So that's it for our ionic radius. So the pattern for ionic radius in the periodic table of element is not stated, but 1A, 2A, 3A. This is on the left, this is on the right. Left, right, left, right. Okay. So it increases from right to left as well. I think more likely. So let's see later. Anyway, variation of physical properties across a period and within a group. So physical properties of elements within a periodic group can be predicted easily given that the elements are in their physical state. Example of a physical property is the melting point. For the element krypton, its melting point can be determined by simply computing for the average of the two elements adjacent to krypton, namely argon and xenon. Okay? So metallic properties of elements vary in a periodic group. Transition of metals to metalloids to nonmetals starts from the leftmost across a period. Examples of these are sodium and chlorine. Sodium, a very reactive metal, is the first element in the third period. On the other hand, chlorine, located in the second to last element of the same period mentioned, is a very reactive nonmetal. So next we have the ionization energy. So again, this is still related to uh, ions. This is the minimum energy required to remove an electron from a gaseous atom in its ground state. It is expressed in kilojoules per mole. Ionization energy is a reflection of how stable an atom's outermost electrons is. As ionization energy becomes higher or the harder for it for an electron of an atom to be removed. Okay, so this is related to the pull of the nucleus to the electrons. Okay, so if the electron is more, or if the atom is more stable, so the pull on that electron is very strong. So the ionization energy is very strong. Since it will take a lot of energy to remove that electron. Ionization energy is classified into first, I sub 1, I sub 2, and I sub 3. An electron is more difficult to remove from a positively charged ion. Ionization energy is derived from an endothermic process since it is expressed in a positive value, and ionization energies of elements have an increasing trend across a period. The ionization energy increases as atomic numbers becomes larger. Okay. This is attributed to the nuclear charge of an atom, wherein, as atomic number increases, nuclear charge becomes stronger and more effective. Okay. In this periodic table, Group 1A elements have the lowest ionization energies. Group 2A have the higher first ionization energies. Electron configuration plays an important role in how strong the ionization energy is needed to remove an electron. Metals have low ionization energy compared to nonmetals, while the metalloids, okay, their ionization energies fall between the two previously mentioned group of elements. Next, we have the electron affinity. Electron affinity is the ability of an atom to receive additional electrons. So this is the opposite of ionization energy. Ionization energy, remove an atom. Affinity, receive. I'm sorry. Ionization energy, remove an electron. Electron affinity, receive an electron. It is also defined as the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. It should be noted that electron affinity is positive if the reaction that happens is exothermic in nature. Consequently, the electron affinity is negative if the reaction is endothermic. It is also expressed in kilojoules per mole. A positive electron affinity denotes the greater capacity of an atom of a particular element to accept an electron. Okay, so these are the electron affinities of some elements. Okay, so let's see the trend in here. Let's see later in the summary how is the trend in terms of electron affinities. So general trends in chemical properties. The chemical behavior of the elements can be determined by knowing their diagonal relationships. This relationship exists between pairs of elements belonging to different groups and periods. Hence, diagonal relationships are the similarities that can be observed from pairs of elements that do not belong to the same group or period. Diagonal relationship can be seen in lithium, beryllium, and boron and their corresponding diagonal pairs in the periodic table. Lithium, for example, shares same chemistry with its diagonal pair magnesium. Okay. So we have some uh, what do you call this one? Summary of our general trends in the per group or the characteristic per group of our elements. So we have hydrogen, since it is the most unique one on 1A. It has a single valence electron, okay, and forms an or uninegative ions. Group 1A elements, it's hard to explain if we don't have a predictable element on this side, right? But anyway, these are alkali metals. They have low ionization energy, they are very reactive in nature, and can rarely be found in its pure form. Group 2A, they are alkaline earth metals. They are less reactive than alkali metals. Their metallic characteristic increases from top to bottom. The reactivity with water varies depending on the element and form of water. The reactivity towards oxygen increases from beryllium to boron. Group 3 elements. All elements except for boron are metals. Metallic elements from both unipositive and tripositive ions. Unipositive ions formed by metals from this group are more stable than tripositive ions. Group 4A. So these are nonmetals. These are the some of the elements included in group 4A. So the carbon here is nonmetal. Silicon and germanium are metalloids. And then the metallic elements of this group do not react with water but react with acids. We have group 6A. Oxygen, sulfur, and selenium are the nonmetals. Tellurium and polonium are metalloids. And they form a large number of molecular compounds with nonmetals. Group 7A. Nonmetals. General formula is X sub 2, characterized by their high ionization energies and large electron affinities. This has the ability to form many molecular compounds among themselves. Group 8A. Atoms of elements in this group have completely filled their outer Ns and Np subshells. These are the noble gases, grouped with the highest ionization energies, also known as the inert gases. They have no tendency to accept electrons. In summary, figure below shows the general trends of elements in terms of their physical and chemical properties. So these tips will help you remember easily the general trends of the different physical as well as chemical characteristics of the elements. Okay, so this one, ionization energy increasing left to right, atomic radius decreasing left to right, non-metallic character and electronegativity increasing left to right, metallic character decreasing left to right, ionization energy decreasing top to bottom, atomic radius increasing top to bottom, electronegativity decreasing top to bottom, then metallic character increasing from top to bottom. Okay? So we have the glossary and then the additional materials on the module. So please take your time and see these materials.